Quentin Yarie. I'm the President and CEO of Macdonald Mines. I'm here with you to discuss our SPJ project, which is a high-grade gold exploration play we're working on in the district of Sudbury, Ontario. Today we're going to focus on some IP results that we collected during January and how those IP results are assisting us with targeting gold mineralization and the events that are controlling the gold mineralization on the Scadding project. So just to put you in reference where we are, the SPJ project is about 40 kilometers east of Sudbury. You can see the property outlined here in blue, the township of Sudbury, and the city of Sudbury located in that area. Obviously, excellent infrastructures in place. The red claims within the blue are the fee simple lands, and that is the area we refer to as the Scadding. This is an aerial view of the Scadding area. Again, Highway 17, 16 kilometers to the south, and we have the Kukugami Road, which gives us all your access to the historic operations at the Scadding mine. For our reference, there's a few things we want to point out here that we need to pay attention to. One is the south pit, the north pit, the east-west pit, and the underground workings. These were the historic workings that last seen operation in the 70s and 80s. Before we go any further, I'd like to explain that the Scadding gold mineralization is a little different than our typical orogenic gold that we are all quite knowledgeable about, or at least experienced with, especially in northern Ontario. If we look at Timmins and Kirkland Lake and the Abitibi, we're typically dealing with gold-bearing quartz veins within a greenstone belt. We follow these quartz veins, and sometimes they have gold, sometimes they don't, but usually, what we're looking for is to identify these quartz veins, which within a larger matrix system, and that's our pathways to finding gold mineralization. The Scadding's a little different. We believe it's part, and I guess it's proven now that it's part of an IOCG type event. And the gold mineralization is associated not with quartz veins, but with iron-rich chlorite veins that sometimes have brecciation, but definitely are a different color and a different makeup from the surrounding host materials, which tend to be albatized. Here's a good example we're showing on the screen. To the south, or to the bottom of the page, not the south, is a very typical orogenic gold deposit. You can see the color. There's lots of quartz veining. A close-up of the gold mineralization you can see is spread within the quartz matrix. And above what we have is an example of the Scadding. And again, the gold mineralization occurs within this iron-rich chlorite, and the host rocks tend to be albatized events, alpha. So why is this all important? Well, we did an IP survey, and what we're looking for is physical contrasts of the rock types and the mineralization that would allow us to better map and understand what's controlling the gold mineralization. It's all about physical contrasts. So typically use IP surveys, which is induced polarization. We measure the resistivity and the chargeability. Well, in the case of the Scadding mine, the resistivity is going to give us a definite vector. The iron-rich chlorites are going to be less resistive than the host rock, which is primarily albatized. As far as chargeability goes, we know that the mineralization of gold at Scadding is associated with other iron-rich things such as pyrite, pyrrhotite, chalcopyrite, and we see some other secondary mineralizations in the form of magnetite, hematite, and sometimes we have cobalt. So that's a little lesson on what we're trying to discover at the Scadding gold mine. So again, just to reiterate what we said about the modified IOCG deposit, and again, the things to take away from this is gold mineralization is contained with iron within titanium iron oxides, which is a little different than we would expect to see at a quartz-rich gold type system. We've had some excellent holes to date. We've drilled 46 holes for a total meterage of just over 7,000 meters. Most of the holes that we're waiting for we've drilled on the east. And we're going to look at all these holes in 3D in context with the geophysics that we collected in January. And again, just to point out the mineralization on the right of the core, you can see the VG occurs with this green type of rock with secondary mineralization in the form of pyrite. Some of the more interesting intersections, I will say. Obviously, we've had some spectacular results, 735 grams over just less than the meter, but also 59 grams over 20 meters around the North Pit area. So this is an area we want to focus on. You can see many of these holes have had, above average intersections of good widths and good grade. And so this will provide us with an example with the IP and resistivity data of what type of events we should be targeting. So what we're looking at here is a plan view of the chargeability data. That's what we have. If you recall, we have the North Pit identified here, the South Pit, and the East-West Pit. There's also the historical underground workings that are shown in this area. If you recall, the Kukagami Road is to the east. It actually cuts through the survey area a little bit, approximately there. Give you scale. You can see this is approximately 700 meter by 700 meters that we did the resistivity survey over. And again, this was a proof of concept for us, and we did it in this area because this is where we had the most data and the most drilling. So the first thing that jumps out at me, if we're looking at the chargeability anomaly, there's a chargeability high that seems to form a circular anomaly, and it seems to be inside the historic pits and sort of in the center. So remember, chargeability in this case would be a measurement of how chargeable the ground is, and usually that's associated with iron content or sulfide content. And we know that the gold at this deposit is associated with iron-rich chlorides. So we would expect to see some relationship between the gold mineralization and the chargeability results. So what we're going to do is we're going to move in and out of this chargeability model, and we're going to look at how it correlates with the gold results. We're going to cut this with the surface, and we're going to look deeper. So we're going to go approximately 100 meters into the earth. What stands out for us now is this circular target still exists, and we can see a better correlation with chargeability and the events we know exist on surface. The other thing that strikes us is there's a series of what appears to be east-west structures that we now know are folds, that this is a tightly folded sequence. We know that from our downhole orientation measurements, as well as observations on the surface where we can see the folding occurring, both at a small scale and a large scale. This is quite interesting to us because I don't think this has been identified before, and it definitely wasn't identified on the surface because it's complicated and it was hard to map. Other things of interest, these folding sequences are cut by a number of northwest, southeast trends. You can see one here that runs typically through the North Pit, the underground workings, and by the South Pit. There's also trends in this area that we can identify. The thing that strikes out to me is these anomalies extend beyond the footprint of the current survey. So that's of interest, obviously, because we will be wanting to expand that. So I'm going to turn off the chargeability anomaly for the moment, and what we'll look at right now in space, in 3D space, these are the gold intersects that we got in our 46 holes. Well, not all of the 46 holes because we're still waiting on results from 3 holes, but this is the preponderance of our own information, and those are associated with holes that we have drilled. There's the holes we have drilled as well as the holes others have drilled within the property. So you can see there's a number of boreholes that had gold in it by the historic underground workings, the North Pit, the Discovery Zone, and with the East-West Pit. So turn off the traces, and again, so what we'll do is we'll take an oblique view of this. We'll turn on our chargeability data. So there's our model. We'll bring everything back up to surface. And so what we can now look at is where those gold results sit within the chargeability data. So we're looking for a correlation of some type. So now we're going to cut through this block in the x-axis. And as we move through, we can see that those values of gold that we see will start to become visible as they move out of the shell. So we can see gold there is associated with a chargeability high. We move along. We get into some of the better information we have here on the gold, and we can see that it is associated with a chargeability high and a low, or at least with a contact. And the same over here is generally associated with an increase in chargeability. So an increase in sulfide or iron content has a correlation with gold values. Now, it's not unique, obviously, that's one of the issues, but we have something else, another physical measurement we can look at, and that's resistivity. And why I say it's not unique is this is a pretty good example. We have our gold mineralization, especially in this area, that's associated with a high and then a moderate value and potentially a low. So there's not a one-to-one correlation of sulfide content or iron content or chargeable items with the gold values. So interesting, good, still provides some targeting information, also gives us some good information on structure and what's going on within the earth. Having said that, we'll now look at the resistivity data. And the first thing we're going to do is look at it in a plan map again, just so we can reference ourselves. So what you're looking at is the north pit, the underground workings, the south pit, and the east-west pit. As we move, starting at surface 325, so we'll go down approximately 100 meters, and we can see these east-west trends become even more evident in the resistivity data. I had suggested earlier that the iron-rich chlorites would be less resistive than the host rock, which is primarily albitized or brecciated. Again, these trends are confirmed and verified by what we see in our borehole orientation data, and also now that we know what to look for, we've been referencing on surface and we can see them. We also notice that those northwest-southeast trends are also in this data set, and obviously the anomalies extend well beyond the survey area or terminate at the edge of the survey area, so we don't know how far they go. Okay, so looking at an oblique view again, and we'll see how the resistivity now correlates with the same results that we had for the gold values. So again, we're going to cut this, moving to the west, and look at where and what the gold value is associated with. So again, we see those gold values coming out. They're associated with a contact between a high and low resistivity feature. That's important, useful. And we'll continue to move through this till we get to our biggest zone or best intersections of gold mineralization. And here we can see that there is an excellent correlation with the resistivity data and the gold mineralization. So though resistivities, because this is a reverse color scheme, have an association with gold mineralization. Well, specifically where we drilled. Remember, we haven't drilled everywhere on this site. These are only the gold intersections that we've drilled. There's also some anti-correlation going on. As you can see over here around the north pit, some of the highest gold values we see are not associated with a high. Again, so that's of interest. So now we're going to have a look at what we came up with to look at this thing. And to do that, I'm going to look at a spreadsheet. So what I did, because historically we would look at something that's called metal factor, and that's simply the resistivity or the chargeability divided by the other measurement. So let's take the resistivity by chargeability. That gives us a ratio. That ratio is generally referred to as the metal factor. The problem with the metal factor is there are no unique solutions. Okay, as an example, we can look at these two graphs as an example. Actually, that's the easiest way. So what we have on this graph is I have plotted gold up the y-axis, and along the bottom we have chargeability. On this graph over here, I plotted gold over the same values against resistivity. So we can see that there is a distribution of gold associated with chargeability, and there's a distribution of gold associated with resistivities. All right. Of interesting facts here, the highest chargeability material does not have the greatest gold content. Also, the lowest resistivity values don't have the highest gold content. But here's the problem with just looking at the two things as is. If we simply ratio these things, obviously a 5 or 5,000 divided by 5 is 1,000, but 10,000 divided by 10 is 10,000. So what I'm suggesting to you is that there's no unique solution. If I divide these, I get the same number that I get here and here versus 5 and 50. And yet we can see there's far more intersects at 1,000 or 10,000 ohms versus 5,000. There's also, at 5 chargeability, there's far more interest for us at 10. Having said that, so what I do to sort of weight these numbers is I take a histogram of the data. I look at the normal distribution of each of these data sets. And in this case, I divided each data set by 10. And I looked at the occurrences within each gate. So I took a gate of a specific measurement, and I said, how many gold values are in there, occur within, let's say, a chargeability of 10 to 12. I would center it around these gates around this. And I would use the normal distribution to weight the ratios. Therefore, I know I'm more interested in a chargeability of 10 than I am of 5, okay? Or of 10 than I am at 40. So what happens is I would assign a weighting value to 10. It'll be around a range again, but around 10. I would do the same with the resistivity values. So, the area of most interest for the resistivity is approximately around 11,000. But again, I would give it a range 10 to 12,000. And now that has a higher weighting in the calculation than 5,000 or some other numbers that occur there. So once we ratio those two, the idea is that now the highest values in the new data set should occur at the areas of chargeability with the most interest and with the resistivities of the most interest. That is the goal. I think in this case it works well. And it works well here because we have this information we're looking at right now. We do have spatial information of gold within the ground in a borehole that we can apply to our resistivity and chargeability 3D models. So what did that give us? So we'll turn off our resistivity and we'll turn on the model. All right, and we're going to go to plan to start with. And I'm just going to show you the entire database. So again, this is, I guess for lack of a better term, we can call this a modified metal factor. But it is specific to this space, meaning space being this data set and this area. It's specific to the scadding site. And again, for reference, we have the north pit, the south pit, and the east-west pit. And again, the circular anomaly still exists. And we can see that there's some trends that extend off-site, which is a little interesting. And again, these northwest, southeast trends are identifiable even at surface. So again, this is at surface. Now, as we cut this down into the earth, so let's go down approximately 100 meters, all the similar trends we saw before exist. Okay, it didn't remove any of these trends, it's just emphasized some that we hope now have a better correlation with gold mineralization. And immediately we can start to see that there is a better correlation. We can see that this gold is associated with a high, as is this, where before when we looked at it, neither data set matched the north pit very well, or one did and one didn't. We can also look in this area and see that there's some correlation here. There is correlation, it's just not at this depth. So that's the thing, other thing we're looking at. As we move up, we can see that surface mineralization is associated with a high. So, having said all that, we'll rotate this over, and we can see how this thing sits in space. And again, of interest, we like the fact that these anomalies extend to depth. I mean, those are good things. We've only drilled to over 220 meter vertical. Here we're modeling, like say, over 300 meters in depth. So definitely we have some targets to the east and to the south to look at. Now, I'm not going to look at the entire data set because what we're interested in, because we've done all this correlation, is we've said we're interested in the highest values that we get from this and how they're associated with the gold mineralization. So we can sort of look at it this way. And again, we're looking at the east. And now I'm going to cut through this block just like we did with the others. Okay, so now we're cutting to the west as we go through here. And we'll pause when we see this gold mineralization occur. So first thing is, if you remember, we had a bit of an anti-correlation here. Now we have a high nicely associated with the gold mineralization that we detected in that area. And obviously we can see that there's some areas of interest we need to look at that have never been drilled. Also, obviously, this anomaly to the south that extends to great depth is of significant interest to us, both from a size perspective and also proving that mineralization extends beyond their current footprint. So as we move through, these gold values are associated with these highs, and now we get into the highest values. And we can associate these gold values. I'm just going to expand this color zone a bit. But these gold values, the highest grade gold values that we see here and around the North Pit, now have a correlation with the geophysical response. So what this is going to allow us to do is to better target gold mineralization. And again, you can see how these things now appear to have a nice relationship with what we see in the geophysical data. Couple observations of this. These things seem to be, the gold-bearing events seem to be subvertical. We can see there's 3 or 4 trends extending across the site, some extending to depth, and so on. The last hole that we drilled is 46, and it was drilled in this area. Just we're waiting on results. And the idea of it was to at least cross this path so we could determine what this anomaly is. I think that's about it for the geophysical IP data. If we look at this, we can see that this is sort of a shell that encompasses the gold mineralization that we have to date. Obviously, to the south appears to be a far better depth target for us, but also we have things extending beyond the resistivity data. Thank you for your time. I hope this has been insightful. And always, if you have any questions, please feel free to reach out by email or call us.